Today, I'm going to be talking to you about a very critical topic for self-driving laboratories. Something that is the brain of most of the self-driving labs that you'll see, most of the ones that are published. And I'm going to do my best to help you understand why we need Bayesian optimization, what it is, what optimization is in general, try to give you the tools and the vocabulary needed to interface with people as well as implement your own solutions. So with that, just a little bit about why we are even interested in materials discovery. Now, I think that most of the people here, just by being at the conference, have some sense of that. But some people come back and they say, what about our existing materials? Do we really need new materials? And my answer is, we discover new materials not because we need to, but because we have the capacity to do so. We can do a lot with our existing materials. We can fine-tune them, we can find new applications for what we already have. However, with new materials, we might find applications for things we don't even know about yet. We might find a better performing material that blows anything else that we've seen out of the water. And I want to talk about an example with Corning ware glass. We have Donald Stuckey here, and I'm going to read this short anecdote from him. He says, "The temperature gauge was stuck on 900 degrees, and I thought I had ruined the furnace. I grabbed some tongs to get it out as fast as I could, but the glass slipped out of the tongs and fell to the floor. The thing bounced and didn't break." So this was the discovery, an accidental discovery of Corning ware glass, this very thermal shock resistant material that ended up being used in rocket nose cones as well. And there are a variety of different methods through which materials have been discovered traditionally. So there are mistakes like with vulcanized rubber and Corning ware glass. Sometimes it's perseverance. You hear about the incandescent light bulb. Alkaline batteries also fall into that category. Sometimes it's just about being in the right place at the right time, like with Teflon. Suddenly, one of their gas cylinders stopped flowing gas. And so what did they do? They sawed it open and found this white powder inside. That was the discovery of Teflon. Other times it's attention to detail, like with stainless steel. I believe it was Canon manufacturing, very early, in the 1800s, I believe. And noticed that in the waste bin, there was a piece of steel that hadn't rusted. And so took a closer look at that. Same with shape memory alloys. Sometimes it's nature inspired, like with Velcro. And this is probably one of my favorites. Sometimes it comes from unsafe lab practices, like with sweet and low. If anyone's familiar with this, the scientist is eating lunch and tastes something very sweet on his fingers. And so he rushes back into the lab and starts tasting all of his vials of target substances, trying to find what this sensory feeling was coming from. And so that's where sweet low comes from. And if you're interested in any more of these anecdotes or mysteries, how are materials discovered? Taylor Smart's great YouTube channel there. And now we get a little bit more into the machine learning data science side of things. So materials informatics can be used to discover new materials as well, in addition to the traditional method. So take, for example, super hardness. This is used in cutting applications. If you think of Elon Musk's boring company trying to drill these giant holes, these tunnels, what needs to go on there? A super hard material that can be resistant to wear. And by predicting some variables that are correlated with hardness, in this case, shear modulus and bulk modulus, you don't need to know what those are, but they're correlated with hardness. They're able to identify two new candidates to super hard materials from that study. And there are many experimentally and computationally validated studies that use machine learning in a material science or chemistry context. And so I encourage you to look at this review to kind of get an idea of what has traditionally been used. And there are a variety of methods that get used here. So we have tree-based algorithms, artificial neural networks, support vector machines, and usually in the limit of low data, we see people using Bayesian optimization. Why? Why do so many people use this? I want to talk a little bit about what's called the drunkard search effect, or the streetlight effect. There's a cop that comes over, he says, "This is where you lost your wallet," And the man replies, "No, I lost it in the park, but this is where the light is." We have this tendency to look where the light is. Think about materials discovery. We make fine, just very small tweaks to existing things, and that can bring a lot of value. We can do this kind of local optimization and find improvements. And we're also pretty confident that we will improve somewhat there. However, not all experiments are equally useful. Some experiments provide more information than others. I love this quote from Citrine Informatics. And adaptive experimentation is a more efficient alternative or version of traditional design of experiments. So with traditional, we've got design and experiments, and then observe all the outcomes all at once. One step, that's the end. Whereas with adaptive experimentation, we design an experiment, we observe the outcome, and then we use that information to inform our next choice, and we continue that in an iterative loop. And I'm going to be talking to you about chocolate chip cookies now. Glad we all had lunch, so we can be a little less, a little more focused on it. So this is an example of design of experiments. You bake N different recipes traditionally, and then you taste all the recipes at once. You wait a day and taste them, but there's no loop there. Versus you bake a batch, a certain recipe, you taste it, you adjust accordingly, and you run that in a loop there. And I want to share a personal story. This example of adaptive experimentation is from a good friend of mine named Marie. And Marie's husband needed to eat some healthier cookies. And so what she did is she applied, she came up with this idea. She took her existing cookie recipe and she gradually reduced the sugar content in there. And day after day, she waited to see what her husband would say. And eventually there came this day where her husband Ron said, "Marie, there's something amuck with these cookies. Something's wrong here." And so she knew, all I have to do is go to the previous recipe, and I'm good. So that's Marie's healthy cookies. And Marie found the optimal cookies using adaptive experimentation. She closed the loop. She used the previous information to inform her later choices. So this is where we're going to get a little bit more interactive here. What are Marie's objectives? So I want all of you to turn to your neighbor, group of 2 or 3 people, and answer this question. So I'm going to put this on you. It should be buzzing with people talking. Turn to your neighbor and answer this. What are Marie's objectives? We'll come back in about a minute.
It's a healthy cookie, right? So you want to make it healthier, but I think that's like just flavor is saying how it makes. Probably look like your friend. I love your outfit. I love the coordination of the pattern with like and the name tag. Like the acceleration name tag. Are you here from Toronto or? Yeah.
Thank you everybody for engaging with group exercise. I love it. So who actually talked about Marie's cookies versus introducing yourself to your neighbors? Okay, cool. Okay, of those people that got to talk about this, can you share? Is there somebody willing to share? What were Marie's objectives here? Up there.
Feasible cookie baking.
Sorry.
It has to be feasible to cook
cookie?
Yes, it does have to be feasible to cook the cookie. Okay, what are other people's thoughts?
It has to be, he wants it less sugar.
Okay, less sugar, why?
For better health.
Yes, exactly. Okay, so healthier cookies. Any other thoughts?
Maybe she's trying to give her husband the same familiar experience at home.
Yes. Okay, and then
Cost efficient.
okay, most efficient. Great. Back there.
I think when you reduce the sugar, then still the whole cookie has to still have the same texture and everything else has to be similar.
Yeah.
So we have to figure out the other how other ingredients compensate.
Great. And then there's a hand right here.
No noticeable impact. on the
Yes.
taste.
Yes.
Noticeable by the husband.
Yes, exactly. So we've got these different constraints. You know, you have to actually be able to make the cookie. We talk about the taste, texture, things like that. So go ahead.
It could be that she wants to make sure that every time she wants to cook, she can make the same cookie.
Yeah. So in optimization, we talk about these as objectives. This is a very key word to learn. I talked about terminology, vocabulary, objective. It has a very specific meaning. And in this case, this all kind of pointed to the same thing. One, the cookies needed to be healthy. Two, the cookies needed to still be tasty. And these are competing objectives. So sometimes objectives are correlated, other times they're competing. This is an example of two objectives, a multi-objective problem. Now, what parameter did she tune? Just show of hands. What's the parameter?
Sugar?
Sugar. It was the sugar content. And so we talk about, depending on your field, you could be talking about design variables, you could be talking about parameters. In machine learning, when you're building models, often you talk about hyperparameters. But these are the knobs that you turn, the variables that you adjust. And what were the constraints on this space? Taste. So when I say constraint, think about bounds. What were the lower and upper bounds on her design space? Go ahead.
Original sugar content or zero?
Yes,
Essentially.
exactly. So 0, you can't have negative sugar, unfortunately. I'm sure everybody would love to add that into their cookie recipes. And then she didn't want to make it any less healthy, any more unhealthy than it already was. So, sorry?
So 0 and 1.
Yeah, 0 up to the original recipe. And so this gives us a search space. We have our parameters and we have our constraints. So search space is another very key term here. Parameters plus constraints equals search space. And a materials optimization task is fully defined by its search space and its objectives. Now, over the last few years, as I've tried to teach Bayesian optimization, and I've run different workshops and tutorials, made lots of videos, this is one of those key points that I say, but it might not stick. So I'm going to leave this up here for just a good 20 seconds and let you think about it. A materials optimization task is defined by its search space and objectives. So please excuse the 15 seconds of awkward silence that I will impose on you. It's hard to be quiet as a speaker. So now I'm going to put it back to you. What is your materials optimization task? Now, we're going to do this again. I want you to turn to the person next to you. Hopefully you've gotten the introductions somewhat out of the way. Hopefully you remember their name from 5 minutes ago. But I want you to turn to them, and for something that's relevant to you, I want you to talk about what your materials optimization task. You can give it in terms of your search space, which includes your parameters and your constraints and your objectives that you're trying to optimize. So take it away. Out here and see this absolute buzz there. It also gives me a very nice break on my vocal. So thank you. So I hope that was helpful. I hope that was interesting. Would one or two people care to share what the materials optimization task of the person they talk to is? Up there, yeah.
I don't really close to this, but Kyle was working on optimizing enzymes, and he was talking about the objectives they have on enzymatic activity and the parameters they have for amino acids. And typically they're trying to maximize the enzymatic activity and minimize the amount of energy to achieve the same enzymatic activity.
Fantastic. And what kind of constraints, and it's okay if answers to, what kind of constraints are on that search space? You talked about the amino acids being the parameters.
We didn't really talk about it, we sort of talked about, like, he said sometimes you'll change one amino acid and then, like, it won't solubilize, or, like, so actually there's sort of non-linear, like, gaps in the design space.
Feasibility, right? Yeah, that's great. Okay, one other person. Yeah, go ahead.
Brad is working on mesoporous silicon nanoparticles, and
he's trying to like adjust the pore size of the material and also the amount of antimicrobial agents that you have on it. So your within, yeah. So the parameters are how big the pore size would be and the amount of antimicrobial agents you have within. The constraints, I guess, would be the pore size would be I don't know the
Particle size.
or the particle size. I don't know the order of the particles he's working with, but it's very small to as big as the particles get, and then 0 to kills all microbes at that level.
Okay, yeah. And what are you tuning? What's the
Release
physical knob? Go ahead.
release rate.
Release rate. Okay.
Okay, so if it's larger pore size, more material gets released.
Okay. Perfect. Thanks. Okay, I think we're gonna move on from there because now we're gonna talk about how you can most efficiently optimize your material. Emphasis on the how. We talked about what your materials optimization task is. And efficiency, in terms of efficiency, when we talk about adaptive experimentation, it's like a tiger cat on the far right versus a hatchet. Now, I'm going to explain a little bit more what I mean by this. So, with grid and random search, grid, 9 points, all in an array, a lattice. Random search, you randomly pick points there and scatter those in. With quasi-random search, we have things like the Latin hypercube and Sobel sampling. And then with adaptive experimentation, we have things like Bayesian optimization. Now, I'm not saying that you should never use grid search or that you should never use random search, that you should always use adaptive experimentation. That's not the case. However, I think there are some key points here. A hatchet is very easy to use. You can cut down a tree with a hatchet. A chainsaw, you have to be a little bit more careful, but I think most people, if you give them a little bit of training, they fire up the chainsaw and they can start chopping down a few trees before they get really exhausted. And then a tiger cat, you can have vastly more efficient clearing of a forest, which you can do sustainably, so I'm not encouraging deforestation here. However, there's some a manual. I'm sure it takes years of training or a long course to be able to learn that. And so my goal here is to help reduce that barrier, reduce that gap to be able to use more advanced tools. So first, let's talk about grid random and quasi-random search methods. So quasi-random search methods have the best of both worlds. And so for 10 points, you can see grid, random, Sobel, Latin hypercube spaced out there. And grid search has systematic gaps throughout the space, whereas random search has large occasional gaps. Now what quasi-random methods like Sobel and Latin hypercube give you are smaller pockets and less systematic. And this trend holds when you move to fewer points. It holds when you move to more points as well. And you can see kind of the grid there, systematic pockets, random, you get occasional large pockets, and then a better distribution on the right. And what I've just been describing to you is related to the term discrepancy. Now, all the discrepancy means is that lower discrepancy means it's more uniform, kind of more evenly spaced across the whole area. And so if we take a look at some of these, the discrepancy value, we can see on the left versus the right, we're seeing about a 10 times increase in discrepancy, otherwise worse uniformity, when we move from some of the quasi-random methods back to grid and vice versa. So in terms of this kind of mathematical measure called discrepancy that measures uniformity, we can see that the quasi-random is a lot better. And let's take a look at why. In one dimension, if we have 3 points and the spacing between them is A, then the number of experiments we have in one dimension is 3. The minimum spacing between any 2 points is 0.5, and the max is 0.5, and that gives us some discrepancy there. Now let's move to a 2-dimensional grid. We'll say 3 points along each dimension, so 9 points. The minimum spacing is still 0.5. The maximum spacing, however, has increased. It's around 0.707, and the discrepancy has also increased. Let's go one more. 3 dimensions. 3 to the third, 27 points. Minimum spacing, still 0.5. The maximum spacing, once again, has increased, 0.87, and the discrepancy has also increased. And so the takeaway here is that the size of those pockets increases as a function of the dimensionality. The higher number of dimensions you have, the worse this problem gets. That's what's meant by the curse of dimensionality. And you can represent this as a formula. When real-world material science tasks, usually we have very few iterations and many dimensions. So let's take the discrepancy. We've got 2 dimensions on the top, 20 dimensions on the bottom. And so running the same thing through, using 100 points, Latin hypercube and Sobel in 2 dimensions, as we showed before, is doing a lot better than grid and random search. However, when we move up to 20 dimensions, this difference becomes very stark, very clear. Where if you have 100 points and you're doing grid search, how do you even distribute those 20 points across the dimension? You're limited to the number that you can choose. And same with random search, you're performing worse than the quasi-random methods. And so discrepancy is useful, but also it's not really what we talk about when we talk about optimization. Optimization is about performance versus cost. And so next we're going to get into this piece. So let's take an example. We've got some function, 2 variables, 1 outcome, and we can plot it in kind of a color heat map. And what Gaussian processes will do for us, the model underneath Bayesian optimization, is we'll get a mean prediction, kind of like a single value that for each point that it predicts. And it also comes with an uncertainty associated with each prediction. Now we combine those two into what's called an acquisition function to be able to help us decide what point we're going to select next in our experiment. So just kind of a brief review, we initialize a search space. That means we define our search space and our objectives. We choose a point, we make it, we observe the outcome, and we repeat that in a loop until we meet some stopping threshold. You run out of money, you get bored or tired, you graduate from your PhD program, etc. And terminology-wise, acquisition functions guide how to explore the parameter space. And then there's this idea of exploitation versus exploration trade-off. Exploitation focuses on the current best results by penalizing for higher variance values. Now this kind of goes back to the streetlight effect, or the drunkard search effect. Exploration, on the other hand, pushes the search towards unexplored regions. And so let's talk about Bayesian optimization a little bit. I'm not going to go into all the math of Bayes' theorem. There's a great 3 blue, 1 brown video out there that you should check out that goes over Bayes' theorem. However, what I am going to talk about is what it looks like, how it behaves. So in blue, we have the mean prediction that we talked about, 1 variable x and 1 function f of x. And the black points are the data that we've observed so far. Those have uncertainty estimates associated with them. And expected improvement is one type of acquisition function that is typically used in Bayesian optimization. And this expected improvement is a function of the model above, and when we plot that, we take the maximum of the expected improvement, the item that we expect to lead to the most improvement, and that's the point that we should choose. And that function is given by the expectation value of the max of what we're observing, minus the best point that we've seen so far, and then we just cut off anything that's negative. We just don't care about that. So that gets a little more into statistics and expectation values. But what happens with this is that we iteratively add new data, recalculate that acquisition function, and complete that in a loop until we meet our end criteria. And benchmark functions are something that can help us to compare performance between algorithms. So I'm going to show you a function. This one's called the Brannon function, but you can just think of it as f of x. It has 2 parameters, x1, x2. They each have certain bounds, so we fully defined our search space. And if we take a look at the log of this function, you can see 3 minima there that went up there. And so we have our fully defined search space. And f of bolded x is really just f of x1, x2. This is just an analytic function for simplicity. And when we take a look at a comparison between all of these, we've got grid search at the top in red, Next we have random search, then Sobel, Latin hypercube, and Bayesian optimization. So for grid, after 20 iterations, the best value that we found, and this was doing lots of repeats and trying to make sure it's very robust, 8.03 for the value. Random search got us as low as 5.04. Next is Sobel at 5.02, then Latin hypercube at 4.2, and then finally Bayesian optimization, 1.89. Gives us about 4 times better than grid search in terms of how low we're able to bring that function, minimizing it. And similar trends hold in higher dimensions. So take a 6-dimensional analytic function, kind of like the Brandon function, but it's called the Hartman 6. The equation's given there just to show you like it's an analytic equation. And similarly, we see that Bayesian optimization in blue, after the initialization points, it starts to get a feel for the search space, it just plummets. It's able to minimize much better than any of the other methods. So we start to see here this curse of dimensionality coming into play and Bayesian optimization helping us to work through it. Now, real-world material science tasks are advanced optimization tasks. So what I've shown you has been the simple cases. First, we can have multiple fidelities. There's this idea of that, I mentioned not every experiment is equal. Well, not every experiment costs the same. We can have simulations, we can have experiments, we can change the parameters that affect how long it takes, the cost involved, and so how do we incorporate this concept of fidelity into our models? We brought up the multiple objectives. We have the health of the cookie, the taste of the cookie. Those are competing objectives. Often we have categorical variables that come into play too. They're not just numbers from 0 to whatever, they're categories. And then we also get constraints in the search space, like everything has to add up to 1. That might seem really simple intuitively, but for an algorithm that can actually be fairly hard to implement in some ways. And it can be high dimensional. What you're looking at right now is a heat map of alloys, all sorts of aluminum alloys, and the different elements that are represented. In total, there are 23 elements represented in that data set. So it's high dimensional, and then we get these kind of weird nonlinear constraints. We talked about feasibility as one. Other times it's parsimony, chemical parsimony. You have 23 elements you can choose from, but you can't just add all 23 at once. Typically, alloys have at most 6, 7, 8 in them in these high entropy alloys. So this idea that you don't want to use all your ingredients at once, just a subset. So takeaways. We're wrapping up here. Not all experiments are equally useful. Marie's healthy cookies is an example of adaptive experimentation. And a materials optimization task is fully defined by its search space plus its objectives. Quasi-random search has the best of both worlds between grid and random. And Bayesian optimization is typically more efficient than traditional design of experiments. And finally, real-world materials discovery tasks are advanced optimization tasks. So, I'm very partial to a particular platform for Bayesian optimization. There are many excellent ones out there. The one I use is Meta's Axe platform. It's built on a stack of tools. Some things I like about it is that there are full-time developers dedicated to this platform, even though it's open source. So that's pretty unique in itself. And it goes through a lot of testing. It's used very widely. If it means anything to you, it has a few thousand stars on GitHub. And it's all built in Python. And it's also based on PyTorch, which if you're familiar with, gives you automatic differentiation. But in terms of this, just think of it, you can run this on a GPU as well to speed things up. And a package that I've been developing that is meant for teaching and kind of reducing that barrier is called Hone Gumi. Now, Hone in Japanese means bones, and then Gumi means a collection of. So this means a collection of bones, which in Japanese translates to a skeletal framework or templates. So this is a framework that I use to help you choose between the different advanced topics. So let's say you have single objective optimization and you've got constraints on that search space, and you want to incorporate multiple fidelities. The idea there, which I'll just jump over real quick if I can. You can kind of see the interface here. So you select what you want in terms of models, and you can interactively adjust what the scripts are, as well as open them in a Google Colab script where you can run it standalone, fully contained. And so hopefully this is a tool that will help you to be able to figure out how to apply it using different tools. And in the next section, part 2 of this, we're going to go more into how to use the Axe platform and apply that to materials optimization tasks. Okay, so that is it. I look forward to seeing you in part 2. There will be a concurrent session focused on that's not until a little later. So part 2, Bayesian optimization, is going to be hands-on in my hall. So we'll kind of amid the break, migrate over there. We'll have some breakout rooms and tables. Please bring your laptops if you have them.